Can you imagine an object with a mass of about 100 trillion suns? Comparing it to our star doesn't help at all to grasp the monstrous size of this star cluster, called Abell C1 1063. It was discovered relatively recently by James Webb, once again proving that the significant amounts invested in the development of this project were well spent. The discovery of such a massive object makes it possible to understand how gravitational lenses work. To find out what Abell C1 1063 is, and to get this photograph, James Webb had to observe one area of the sky for 5 whole days. A telescope has never focused on a single object for this long in observation history. Fortunately, James Webb is equipped with the best modern equipment, including a highly sensitive infrared camera. So, what do we currently know about the supercluster, Abell S1 1063? It is located in the constellation Grus at a distance of about 4.5 billion light-years from Earth. According to recent data, this cluster contains 51 galaxies. But these are only the confirmed objects, and it is believed that there are more than 400 unconfirmed ones. So this enormous mass acts like a cosmic lens, distorting and magnifying the light of more distant galaxies. The cluster has been observed before, and it shouldn't be. A few years ago, it was studied by the Hubble Space Telescope as part of the Frontier Fields program. However, James Webb provided more detailed and clearer images taken with near-infrared camera. It's worth telling a little about this unique research tool. The near-infrared camera is the heart of the James Webb Telescope. It is this camera that can accurately detect areas of active star formation and discover exoplanets, no matter how far away they are. Why is near-infrared camera able to do this? First of all, it's thanks to its design. The camera is specifically built to capture images that are hidden from direct observation, such as galaxies or stars shrouded in dust clouds. Another important feature is the presence of coronagraphs. They block out the overly bright light of stars, which allows the camera to detect faint objects near those stars, such as exoplanets. The camera is also equipped with a spectroscope. Thanks to this, it's possible not only to see the object, but also to analyze its spectrum, determining the temperature of the observed star or planet, its speed, chemical composition, and redshift parameters. Near-infrared camera operates in 2 ranges, which expands the functionality of the instrument. The camera is also equipped with a number of filters that help study different types of objects. Interestingly, this instrument can function satisfactorily at extremely low temperatures. For the detectors, it is minus 233 degrees. This is an important aspect in the conditions of the space vacuum. That is why James Webb achieves unprecedented success and keeps discovering new and new sensations. Nothing in the universe can hide from the attentive lenses of its camera. He, like Harry Potter, can pass through dust walls and reach the truth. What scientific value does the gravitational lens studied by the telescope have for astronomers? Just like an ordinary lens gathering dust in the top drawer of your desk, it magnifies objects many times over, allowing us to see even those that the most sensitive optics couldn't detect before. That means we'll be able to observe galaxies we never even dreamed of studying before. For example, those that appeared almost immediately after the Big Bang. Why are scientists so interested in closely observing gravitational lensing? The thing is, this amazing phenomenon is indirect evidence of the existence of dark matter, substance that we can't see, but it reveals itself through enormous gravity and mass. As for the Abell S1 1063 cluster, after the data obtained from James Webb's observations, astrophysicists are confident that the structure is in the process of merging several galactic clusters. In other words, the period of the cluster's existence that we are observing now is quite active. The confidence that these assumptions are correct is reinforced by research from the Chandra telescope, which has detected very bright radiation in this area, confirming the presence of merging processes. What other details caught the attention of astrophysicists during the observation of the galaxy cluster, Abell S1 1063? Maybe this amazing sound. Or maybe the stunning effect known as the Einstein ring. In this case, the second is correct, although the first one is probably true as well. In such an ancient, distant location, there is almost certainly something frightening and mysterious hidden, capable of making such sounds. However, let's return to the scientific assumptions of Doogie Einstein. This is a clear effect of gravitational lensing, which the famous scientist predicted in his theory of relativity. These arcs look like bright, elongated bands or rings of light produced by very distant galaxies. The effect is a curvature of space-time, predicted many years before we saw it with our own eyes. That is, it's important to understand that Einstein arcs are not a physical object, but rather an optical effect that allows us to study incredibly distant galaxies, which would be very dim without this gravitational bonus. It turns out we've finally lived to see an era when theoretical predictions come to life and become observable. We tested the first effect predicted by Albert Einstein long ago, and now adjust for it in satellite navigation systems. We're talking about gravitational time dilation. The most striking example is falling into a black hole, but there are less traumatic ways to prove the existence of this effect. For example, the Haefel-Keating experiment demonstrated the reality of the twin paradox. As part of this experiment in the fall of 1971, the scientists whose names the experiment bears made a trip around the world with cesium atomic clocks on board an airplane. After that, they compared the readings of the chronometers with the clocks that remained stationary and peacefully stayed at the United States Naval Observatory. As a result, the stationary clocks ran faster compared to the traveling ones. This effect is necessarily taken into account in navigation systems, otherwise there can be no talk of accurate geolocation positioning. And these are just two confirmed scientific predictions. Can you imagine what awaits us in the future? Do you want to drink the elixir of eternal life or trust your body upgrade to nanorobots to see all this with your own eyes? Let's move on. The discovery of the Abell S1 1063 cluster with its staggering gravitational effect is just the tip of the iceberg. But what was found using lensing is not only surprising, but also inspires awe. Meet Galaxy MOMZ 14. At the moment, it is the oldest one discovered. James Webb measured its redshift parameters, and it turned out that the object's age is about 13.5 billion years. That's how long the galaxy's light took to reach us. And this, in turn, means that right now, we are observing a star cluster that appeared about 200 to 280 million years after the Big Bang, during the reionization period. Everything would be fine, except this was when neutral hydrogen had just started ionizing from energy emitted by the oldest celestial bodies. The appearance of such significant conglomerates, according to existing scientific theories, is impossible. Most likely the galaxy you see in the photo now is equivalent in size and mass to the Small Magellanic Cloud. The discovery of the object located in the constellation Sextans happened quite recently, in 2025, and once again became possible thanks to the universal NIR CAM instrument. Before the arrival of James Webb, it was absolutely impossible to see such distant structures, even with the help of gravitational lensing. Judging by the observations, the galaxy is going through a period of active star formation. Perhaps this is another factor that helps us see it. However, the cosmic lens created by the massive cluster Abell S1063 also significantly helped in the discovery of the galaxy MOMZ 14. Without it, such a distant object would be inaccessible for observation, and even more so for study, even with the state-of-the-art equipment of James Webb. But the main thing is the result. Now we know much more about how and when the torch of our universe was ignited. The data obtained require us to update our existing information regarding the evolution of galaxies and the structure of the macrocosm, as well as to develop new conceptual approaches to their study. What is Abell S1063 at the moment? Is it a distant star cluster acting as a gravitational lens? That's what's on the surface, but in reality it's the largest tool for studying the early universe, as well as the hidden properties of dark matter. Perhaps soon, we are in for a real cosmological revolution, a radical revision of traditional theories, and the destruction of pillars of physics that once seemed unshakable. In any case, humanity is only at the beginning of the journey, since the period before this was more like laying the foundation of science. But now, with ultra-modern telescopes like James Webb in orbit and operating, an era of more serious observations and realistic predictions is beginning. Join the Hubble channel and stay updated on space news. We always have the latest updates.